All right, as we continue on, we mentioned and showed that if I have two angles, whether it's angle side or angle side angle, those are good candidates for using the law of sines. Very straightforward, very easy. A lot of times in physics, that's the example that you'll use if this is taught in a physics class. I showed you in the last video that SAS would leave us with too many unknowns in the wrong places, and that's also true if I have all three sides. If I knew this was 5, 6, and 7, but I didn't know any of the angles, no matter what combination of ratios I had to make a proportion, I'd still have two unknowns. Law of cosines is going to help with both of those cases. The third case, though, is what happens if I have a triangle and suppose I know two sides and an angle that's not included. So let's call this one 30 degrees. This is a good candidate for law of sines because I can say, let me put some, call this, let's go an x here, a y here, and make this side z. So if I say the sine of 30 over 7 is equal to the sine of angle y over 6, when I cross multiply, I'd get 6 times the sine of 30 equals 7 times the sine of y. And this would give me 1/2 times 6, or 3, divided by 7. And so if I put in my calculator and do the inverse sine of 3/7, I get that y is approximately equal to 25.377 degrees. Okay? That should make sense, because notice, if it's across from the 6, it should be smaller than the angle that's across from the 7. I could then take those two together and say, hey, it's roughly 55 degrees. Subtract from that, I get 125, or to be more exact, I'd get that x is 124.623 degrees. And then I could set up law of cosines again with sine of 124.623 over z equals the sine of 30 over 7. Now, this brings up an interesting point. When possible, you only want to use values that you're given. Okay? So when I figured out what y was, I used the 30, the 6, and the 7. But at some point, if I wanted to find what z was, I needed to use this calculated value. Okay? You want to avoid that as much as possible, but sometimes it's inevitable. But I still would say the sine of 124.623 over z is equal to the sine of 30 over 7, as opposed to doing the sine of 25.377, because I'm rounding. The more often I round things, the more often I'm going to make a mistake. Okay? This is a good candidate. We did that. That's great. Works fine. But it would be a lot harder if I take the same example and instead move the 30 degrees over here and move the y here. Okay? So if I'm given two sides and the angle that I have is an acute angle across from the smaller side, there's what's called the ambiguous case. And your book, I think, does a great job on page 481 on the left-hand column of showing a couple of, hey, this is why something would be ambiguous. And so I recommend that you look at their drawings because it's going to be a lot better than mine. Well, let's see what would happen. If I said the sine of 30 over 6 equals the sine of y over 7, in this case, when I cross multiply, I get 7 times the sine of 30, which would give me 7/2, equals the sine of y over 6. And, sorry, that should be the sine of y times 6. Then when I divide both sides by 6, this would end up giving me the sine of y is equal to 12. So after doing cross multiply and divide, you should get that. Now, the issue comes in here. If I do 7 divided by 12 and take the inverse sine, I get y is approximately equal to 35.685 degrees. And that's true, and that's good, and I can do things where this is going to be a small angle and things open up wide, and z is definitely the biggest side in the triangle. But there's also a case where maybe the 7 is the biggest side in the triangle. If you remember from All Students Take Calculus, if I have an angle between 0 and 90 or between 90 and 180, I'm going to get a valid value of sine that's equal to some positive number. So it's possible that I can have a second quadrant angle, or an obtuse angle, in other words, that's going to have a sine equal to 7/12. So I have to also consider that there's a case where y is equal to 180 minus that, which should be 144.315. Okay? Now, would that still work if I already had a 30-degree angle? Yes, because 30 plus 144 is 174. So then angle x, in this case, would end up being 5.685 degrees. In this case, the angle x would be, let's see, 65, 180 minus that, 114.315 degrees. So I get a totally different value for x, and then if I do the law of sines again to figure out what z is, based on this x value, it's going to be completely different. These are both correct answers. Okay, it's two different triangles. Again, please look in your book. There's a really nice drawing on the left side of page 481 that will show you that. Okay? Now, it's also possible when you're setting things up that you get an answer that just doesn't make sense, and the law of sines will help you to see that. So it'll give you an invalid triangle. So if I had an example like this and I said, hey, this is 7 and that's 6, and I said that this is 95 degrees. Okay? Well, remember, the small side's across from the smallest angle. There's no way I can have another obtuse angle. That's the biggest angle in the triangle. So I can tell you just by looking at it that this isn't going to work. But if you didn't know that and you said the sine of 95 over 6 equals the sine of x over 7, when you cross multiplied and divided, you'd end up with the sine of x equal to, let me put it in the calculator real quick, 7 times sine of 95 divided by 6 equals 1.162 something, something, something. You should remember that the range of sine is between -1 and 1. That's too big. If I go ahead and put that in my calculator, it's going to give me an error. And basically it's that this triangle cannot exist. So there are times that you can use the law of sines and it gives you no triangles. The majority of cases, like this one, and the first one I did in this video, give you one triangle. And there are cases, and it's always when you have an acute angle across from the smaller side, that the bigger side could be across from an obtuse angle, or maybe not, that it's possible to have two. So that should be all the fun with the law of sines.